Yes, good morning, doctor. It's my presentation. And my research proposal that is explainable cloud forensics for virtual machines in heterogeneous distributed data centers. That's the content. Introduction. Cloud computing, the delivery of computing services and resources over the internet. Cloud computing services are, are, are being provisioned or provided to the consumers by the cloud service providers. Statistically stating that 90% of the businesses have embraced or they have adopted the cloud computing services. And 33% of those services are being dominated by Amazon Web Services. 32% of them services being provided by Google Cloud, and then 22% by Microsoft Azure, and then 10% by Google Cloud. So this is statistics showing the global cloud computing market share, and it's being dominated by those three companies, and 35% being dominated by the other companies like Oracle Cloud. Now, due to the increased need for cloud computing services, cloud data centers have also emerged. And we see that the data center growth has moved from 26.6 billion US dollars to 69.4 billion US dollars. That's the projected amount of money in terms of cloud center growth. That is the projected amount of money in terms of cloud center growth projected to attain in 2033. Now, this graph here shows the cloud security incidents that have happened in 2024, with phishing attacks dominating, and then this other graph here shows the cloud market share of the other the three companies dominating. That is Microsoft Azure, Google Cloud, and Amazon Web Services. What are data centers? Data centers, these are the facility that is organized to store enormous amount of data for the users, and also deliver IT resources to the consumers. So they provide a shared pool of resources and applications for the people to perform their normal computational tasks or their normal business tasks. So data centers, they have components that makes them up. We have all the primary components. That is we have compute, network, and storage. Those are the primary components that make up a data center. And then the physical infrastructure is made up of servers, storage systems, RAID, switches, UPS, SCs, and other components. Distributed data centers. Distributed data centers, those are these are data centers that are geographically distributed in various in various locations, dedicated to provide IT services, but built on the primary components of compute storage and networking. This map of Uganda shows the 6 geographically distanced data centers for MTN. MTN has six data centers, physical data centers, dedicated to provide services to the population. These data centers bring services closer to the people, like in terms of making calls, mobile money transfers, etc. The centralized data centers, those ones provide IT services, resources, and they are dedicated to provide those services within a single location. Data center types, there are very many data center types. There are actually 4. We have the enterprise data centers, co-location data centers, managed data centers, and cloud data centers. This is now cloud computing architecture. So this is the architecture that makes up a cloud computing system. At the bottom here, we have the physical layer. The physical layer is like the on-site premise of the cloud service provider, where all these other resources or services that are being provided to the people are coming from. So the cloud service provider is at this level here, and then a single host. Then from here, after this port here, there is virtualized layers. Now these are layers that provide abstraction and provides. They create instances of hardware or software that can be used to provide cloud computing services. Now at the top here, we have the cloud computing layer. Now this is the layer that provides the services to the people. For example, this layer can be used to provide the application that performs big data and analytics and so on. So this is the cloud computing architecture. Then heterogeneous distributed data centers. Now heterogeneous means combines very many technologies, computational resources, etc. So it provides various computational resources to geographically separated users. These computational resources can include hardware, software, deployment models, etc. A heterogeneous data center can also have different service providers or cascaded cloud service providers. This is a visualization that shows heterogeneous distributed data centers. So we can see here a user in Lila, for example, is accessing a hybrid cloud and is performing, or is being provided with a software as a service to perform e-commerce. E-commerce maybe wants to sell his goods online and wants to have those day-to-day transactions. So an e-commerce platform is being provided to him, and he can also is also performing all these other tasks, computational tasks like video streaming. Then there is this other hybrid cloud data center in Mukono that is providing to these users a platform as a service. For example, they are maybe running, they are developing AI systems. So now here the central orchestrator provides them with the hybrid cloud, and then they perform the ML and AI they develop AI systems using those applications of AI and ML applications using the platform as a service cloud service model. So here you see that different users here are being provided with different computational resources from a central orchestrator running an OpenStack cloud computing platform. Cloud forensics, it's a term that is borrowed from two terms, that is cloud computing and digital forensics. So cloud computing, we saw that definition. Then cloud forensics is the use of scientific methods to identify, preserve, examine, collect, analyze security incidents that have happened in the cloud environment for admissibility and presentation in the courts of law. So we need to identify some of the crimes that have happened within the virtual machines, because this research is specifically emphasizing on virtual machines that are deployed on the cloud. These are examples of cyber crimes that have happened. For example, of recent, the attackers from Asia attacked the Bank of Uganda's IT infrastructure, and they stole 62.4 billion shillings from the central bank. So these are some of the cybercrime incidents that have happened. Background of the problem. Traditional methods such as the signature-based. These methods are methods that are used to extract evidence or to detect crime-related activity within the cloud environments. But these methods are too slow, because to carry out cloud forensics using forensics toolkit on a clone disk of 122 GB and 2 terabytes would take 5.5 hours and 85 hours respectively. So this shows that these methods are slow as far as evidence detection and retrieving crime-related data in those within the cloud environment is just quite challenging. There is also what we call these other traditional methods like the signature and the rule-based. Those ones, they are also slow, and they also rely on, or they are built on a set of predefined set of known threads or signatures. So they suffer so much in detecting new patterns of attacks that exist in a cloud environment, because the cloud environment consists of new data that keeps on flowing in. That new data that keeps on flowing in can also incorporate new patterns of threats. So these traditional methods, they are built on a database of known threats, so they can suffer at detecting those threats, leading to a high false positive rate in the context of detecting those anomalies in the cloud system. We need also to develop models. So because of those problems, because of these problems that are emanating from traditional methods, we need to develop deep learning models that can be used to detect evidence from the cloud that are very fast with a high detection accuracy. Okay, and also and also build the interpretability and the explainability, because these version methods, they lack the interpretability and the explainability component that help in building a trustworthy digital forensics framework. Problem statement. Now, because the cloud environment consists of the data that's being generated from it, for example, as we saw from the other heterogeneous distributed data center, there's too much data. The inflow and outflow of data, there is too much data that's being generated. So generating evidence from that data, from that kind of environment, heterogeneous environment, it's a challenge. Generating data from such an environment for crime-related behavior detection, it's a challenge. The cloud nature, the cloud computing environment consists of various components. For example, multiple data centers, data duplication, multi-tenancy, and the various layers of virtualization. We saw those various layers of virtualization. So it becomes a complex task to perform forensics activities in those environments, or in that environment consists of those layers. Main objective: to develop a forensics framework aimed at detecting and identifying crime-related behavior from the virtual machines spread across various heterogeneous distributed data centers with the help of explainable AI. Objectives: to identify the status of the VM instances in the cloud, to identify them as either affected or normal, such that we can easily detect evidence from those infected ones or the attacked ones, to identify features needed by forensics analysts for evidence detection in the VM, to train, build, and evaluate the planning models for evidence detection from the VM instances, then to implement explainable AI using Lime and Sharp. Significance of the study. This framework will help to bypass the various layers of virtualization, the components actually of the cloud computing platform that is consist of multi-tenancy, and then the physical data, because physical data access means that the cloud forensics investigator will not have to travel from one place to another collecting evidence. So, we shall have to develop a framework that will bypass those limitations, so that we can analyze and generate crime-related activities from the VM instances. Then identify to be used by stakeholders to identify insider and outsider threats. And it also help to help institutions to develop strong security systems and defense mechanisms. It also helps to provide explainers to the cloud forensics analysts to quickly understand how deep learning models come up with such predictions for large data sets. Literature review. This paper here, it shows various works in the field of detecting threats and anomalies in the cloud-based environments. So they use the number of deep learning models or machine learning models to detect distributed denial of service attacks. So they use the some of the methods are like the voting extreme learning machine, the random forest, the support vector. They also use their this paper shows various also literature that shows that they use deep learning models like the deep preferred neural network combined with a freeze-tail elephant herd optimization. And it shows that these models performed well in terms of accuracy, precision, and recall as far as detecting evidence or detecting disciplinary service attacks is concerned, as compared to the conventional traditional methods. This other paper used a CNN. CNN was used to detect or to classify data within a cloud computing environment as either benign or malicious using as a convolutional network within the virtual machines. Now here, this model here performed well in cloud or virtualized environment. It didn't perform well in virtualized environment, but it performed well in non-virtualized environment, providing a detection accuracy of 97.95%. This other paper here, they implemented what we call a hybrid anomaly detection model that combines what we call gray wolf optimization and improved gray wolf optimization and the CNN to detect malicious activities in the cloud, or it classified various attacks, and this CNN improved Go or grow of optimization was used to extract relevant features that can be used for the CNN training. And the CNN training was built on DAPA 998 and KD98 and synthetic datasets. So the improved growth optimization achieved greater accuracy than the traditional methods, than the traditional ML methods, these ones. This also other literature. Because of time, I'm not going to go through them all because okay. Now this one used they developed what we call an internal and external introspection system that is used to introspect the activities of the virtual machine using a VMI with memory forensics analysts with machine learning, and this system was built on 6 classifiers, and we found out that the random forest among these 6 classifiers, the random forest was the best at classifying the data as benign or malicious, with achieving detection accuracy of 95.55%. Now, this other paper gives us knowledge about the challenges, methods, and tools and approaches that are applied in the field of digital forensics within the cloud and social media networks. So some of the tools like the evidence, the magnet internet forensics evidence finder that is used to remotely extract and analyze crime-related evidence. But now these methods here, they are slow at detecting evidence or retrieving evidence, and because they use the other methods, traditional methods of manually searching and indexing the data in order to extract evidence. Data set description. A private cloud was installed on the computer system using an open cloud management platform. There is the Leopard API was used to generate the KVM data by extracting log information of the VM at an hypervisor level. Then the VM instances are labeled normal and attack, meaning that the normal means that those are not compromised. Then the attack ones means that those VMs are compromised. This is the methodology. Data pre-processing. So we shall have to clean the data set, removing irrelevant features. Then do some data transformation using the minimax scaler and balancing the data set using SMOT. Then we shall do an EDA. Then we shall have also to generate a heat map that shows the positively correlated variables and the negatively correlated variables. The heat map will help us to extract relevant features that can be used for the deep learning model training. Deep learning models I plan to develop. I propose to develop the feed forward neural network, CNN, LSTM, and RNN. That's the architecture. Model training, model building and training. So I'll build the modules using the architecture, this architecture. Then I'll have to train the models using the train 80% training and 20% testing. Then after that, I'll train these models across 50 epochs. Then I'll have to test the models and evaluate them using the various evaluation matrices on the 20% data set, using the matrices of precision recall accuracy and F1 score, or construct an AUC or receiver operating characteristic curve. Shall have also to construct a confusion matrix to identify the true negatives, false negatives, true positives, and false positives. Application of explainable AI. After testing those models, building them and evaluating them, then we shall have to perform an explainable artificial intelligence using Lyman Sharp. Now, the AI, artificial intelligence, explainable artificial intelligence will help explain how those models come up with this prediction. For example, why is it predicting that, for example, a VM instance deployed on the cloud within a heterogeneous distributed data center? Why is that VM is predicting? It is predicting infected, or it has been attacked. What are those features that are causing to that fact that that VM has been attacked? What are those other features that? So those ones will provide explainers to the artificial intelligence experts in order to extract evidence that can be used to, and also these ones will also help us to establish a connection between the independent variable and the dependent variable. So by that, by those explanations being generated by the explainable artificial intelligence, to help to generate comprehensive reports by the crime forensics analysts and security experts that will be presented in the courts of law. Mapping specific objectives, that these ones I've already explained some of them. For example, what are the methods I'm going to use to implement explainable AI? using Lyman Sharp. So we shall have to instantiate Lyman Sharp explainers and construct visualizations, waterfall plots, local and global interpretation plots, Lime local feature importance graphs. These are some of the tools which I'm going to use in order to display the actions and the workings of the explainable artificial intelligence, how they come up with those predictions. These are the references. I beg to stop here. Thanks for your kind attention, Doctor. I beg to stop here. Let me stop this.